Good afternoon, class. Welcome to EGM 212, Engineering Mathematics 2. And the topic this afternoon is linear differential equations with constant coefficients. The typical form of the general linear differential equation is given as shown, where x can either be a function of x or equal to 0. The x that is appearing at the extreme end of the expression can either be a function of x or can be equal to 0. So there's a difference. The capital letter x can stand for a function of x or can be equal to 0. And the P0, P1, P2, right up to Pn, these can either be functions of x or constants. They can either be functions of x or constants. So when in the above equations, the values of P are all constants, then the equation is said to be linear differential equation with constant coefficients. We just mentioned here to say the values of P0, P1, P2, right up to Pn can either be functions of x or constants. Now, the case in which PO or P0, P1, P2, right up to Pn are equal to constants, that equation then becomes a linear differential equation with constant coefficients. In this lesson, we shall begin with equations of the second order, which take the form d2y over dx2 plus a dy over dx plus by is equal to 0. So in this lecture, our discussion will involve mainly, let me just select a pointer. Okay, so in this lecture, we shall discuss second order equations that will take the form I've highlighted here. d2y over dx2 plus a dy over dx plus by is equal to 0. Let's look at the symbolic representation. Symbolic representation. The equation d2y over dx2 plus a dy over dx plus by is equal to 0 can be represented in the d notation as d squared plus ad plus b. Then in brackets, outside the brackets, you have y is equal to 0. This notation, the representation of the given differential equation in this form is what we call the D notation. The D notation, where D stands for the differential operator. The differential operator. So now, what does this D stand for? So for a single differential coefficient where you differentiate once, like in the first case here, dy over dx is equal to dy. dy. So this implies that if we remove the y from this differential notation, then here we'll remain with the d only. The y will also leave here. So in other words, the d alone stands for d over dx. So equally for the second differential coefficients, we have d2y over dx2 equal to d squared y. This is what we call the D notation. So for higher orders, we can see that the third differential coefficient, or if you differentiate 3 times, d3 over dx3 is equal to d cubed. So there's supposed to be a y here, which was omitted. Yeah, there's supposed to be a y. So d3y over dx3 is equal to d cubed y. Then for the nth order, we have dn over dxn equal to d raised to the power n y. So the y, there is supposed to be a y here as well. Yeah. So these are what we call the D notations. These are simply ways of representing differential equations. Okay. Let's move to the next step, the auxiliary equation. Suppose in the same equation that we just checked on the previous slide, d2y over dx2 plus a dy over dx plus by is equal to 0. Suppose in this equation we are given y to be equal to e raised to the power mx. Suppose in this differential equation we are told to say y is equal to e raised to the power mx. Then we have this expression, d2, then e raised to the power mx over dx squared plus a d over dx of e raised to the power mx plus b, then open bracket, e raised to the power mx is equal to 0. So in this equation, what we've done is that we've simply replaced where there is y, wherever there is y in the given equation, we've put e raised to the power mx. So this e raised to the power mx has replaced all values of y in the given equation, and therefore the resultant equation looks like this one here. So having performed the differentiation in the first two terms, you realize that m squared plus am plus b in brackets, outside the brackets you have e raised to the power mx is equal to 0 will be the resultant equation. After performing the differentiation, you arrive at this equation. Then, from this equation, we know to say the value of y is equal to e raised to the power mx, and this value of y cannot be equal to 0. And it is not equal to 0. So therefore, in this equation, the m squared plus am plus b brackets e raised to the power mx is equal to 0. We know to say if e raised to the power mx is not equal to 0, then it means the roots for m squared plus am plus b should be able to give us a 0. If we multiply, they should be able to give us a 0. Okay, so now let's see the next step. So since we've just mentioned, we've just made it clear to say y cannot be equal to 0. If y cannot be equal to 0, and we know that the product of y and what is in the brackets should give us a 0, then it implies that m squared plus am plus b should be equal to 0. So we are now supposed to find values or find the unknowns in this equation that will make this statement to be true. So those unknowns should make this statement to be true. Okay? So let's move to the next statement. So the m squared plus am plus b is equal to 0 is what we call the characteristic equation. M squared plus am plus b is equal to 0 is known as the characteristic equation. I guess we've seen where it has come from. It started from the differentiation of this differential equation. We differentiated, then it yielded this equation. Then after that, we started to say, since the value of y cannot be equal to 0, and we know to say the product of this same value of y and this quadratic function should give us 0, then it is very clear, actually, that the m squared plus am plus b should be equal to 0. So this resulting equation is known as the characteristic equation. We call it the characteristic equation or the auxiliary equation. It's one and the same. Characteristic equation or auxiliary equation. Then the roots or the solutions to this characteristic equation or the auxiliary equation, the roots of this equation are known as characteristic roots. Characteristic roots. So like in this case, the values of m, because this characteristic equation has given us a quadratic function. This is a quadratic function. So you can get the values of m by either completing the square method, the formula method, or indeed the simplest, which is factorization, if the arrangement of the values is friendly enough. So the above auxiliary equation has got two roots because it's a quadratic function. So it has two roots, m1 and m2. So since it has two roots, then we expect that it will have two independent solutions. So the first one is y equals e m1x, and the second one is y equals e raised to the power m2x. So we've seen the values of m1 and m2 are the roots or the characteristic roots of the auxiliary equation. So now, to get the general solution of the equation, we simply combine the two independent solutions. So we have y equals c1 e raised to the power m1x plus c2 e raised to the power m2x. So that is y equals c1 e raised to the power m1x plus c2 e raised to the power m2x. So now, one would ask to say, where has the C1 and the C2 come from? The C1 and the C2 are simply arbitrary constants. These are constants. That's why this equation, we are calling it the general solution. The general solution. So there are these unknowns that can only be got if you are given some conditions. I think as we progress in the topic, we'll be able to come across some situations where we will be asked to calculate values of these constants. So this is the final expression for the general solution of the equation. Okay, so now here we are assuming that the roots are real and unequal. the roots or the solutions to the characteristic equation or the auxiliary equation are real and unequal or different. This is the general solution. So the nature of characteristic roots of an auxiliary equation determines the expression for the general solution of the differential equation. The nature of characteristic roots of an auxiliary equation determines the expression for the general solution of the differential equation. Let's look at the different types of roots that we are likely to expect. So there's this statement here, very important. Below are procedures to follow depending on the nature of roots when determining the general solution for a differential equation, which is of this form. So for this case, we've depicted a format where the right-hand side of the equal sign is equal to 0. So the differential equation where the right-hand side is equal to 0. So this is the general representation. So the first case, if the roots of the characteristic equation or auxiliary equation are real and different, if the roots are real and different, then the general solution is given by this formula. This is an expression. Y equals C1E M1X plus C2E M2X plus C3E M3X plus, then it goes on up to CNE MNX. So this expression is generally written, it takes into account the many types of, many roots that a characteristic equation is likely to yield. So if it has 2 roots, then this equation will just end here. If your characteristic equation has got 2 roots, then your solution will just end here. So if it has 3 roots, it goes up to that stage. So it goes on and on depending on the number of characteristic roots that you find. Okay, let's look at the second case. If the solutions to the characteristic equation are real and equal, if the solutions are real and equal, then the general solution will be Y equals C1E M1X plus C2X E M1X plus X squared C3E M1X plus, it goes on right up to the nth term in terms of the constant. Okay, so this is the case when the answers are real and they are equal. So for 2 terms, you end here, like the case we've just discussed on the previous slide. Let's look at the third and final nature of roots that we are likely to encounter. So for complex or imaginary roots, that is, if roots are of this form, I guess you do remember complex numbers in EGM 211. I think you must have covered that. Yeah, so here I, the complex number I, stands for the square root of -1. The square root of -1. Then you realize that for those of you doing electrical engineering, instead of using I as we use in mathematics, I'm sure you must have used the letter J. So the meaning is just the same. Then one would ask to say, why do we use J in electrical engineering and not I? So this is simply to remove, to get rid of the ambiguity. Because in electrical engineering, we use small letter I to represent the instantaneous value of current. So researchers had to think of using a letter that comes after I, which is J, to represent the complex number, which is the square root of -1. Okay, so now when faced with a characteristic equation that yields complex or imaginary roots, the general solution is given by y equals C1e raised to the power a plus bi in brackets x plus C2 then e in bracket to e raised to the power in brackets a minus bix. Okay, so these two, you've seen that the superscript complex numbers are conjugates of each other. So for the first one, there's a plus, then the next one, there's a minus. So this continues to C1 e raised to the power ax cos bx plus C2 e raised to the power ax sine bx. This is the expression for the general solution of a characteristic equation that yields complex numbers. Okay, let's look at an example. So for this example, we're saying solve the equation. We have d2y over dx2 plus 7 dy over dx plus 12 y is equal to 0. So solution, first we express the given equation in the D notation. So this is the second differential coefficient. So we say d squared plus 7, which is the coefficient here. Then dy over dx is simply represented by d, then plus the constant 12. Then in brackets, we take out the y, this y. So this y is common to all the three terms. So it's factorized out. So it comes out, then we equate it to 0. Then from this stage, we know that y cannot be equal to 0. Then we now come up with what we call the auxiliary equation. So how do we get the auxiliary equation? We simply replace, this is the simplest method. We simply replace d with m standing for the roots. So having converted the given equation into the D notation, then from the D notation, we replace the letter D by letter M to come up with the characteristic equation or the auxiliary equation. So this particular one is giving us m squared plus 7m plus 12 is equal to 0. So if you use whatever method you use to factorize, you realize that it will give you m plus 3 in brackets, then again m plus 4 in brackets is equal to 0. So this implies that m plus 3, the first term, m plus 3 is either equal to 0 or m plus 4 is equal to 0. So it's either m plus 3 or m plus 4, which is equal to 0. So both terms are equated to 0 in order to get the value of m. So equating m plus 3 equal to 0, equating m plus 3 to 0, we get the value of m as -3. So the first m here, we can put a subscript 1. m1 is equal to -3. Then the second value is m2. m2 is equal to -4. Then for the general solution, we simply recall our earlier expression where we say y is equal to c1e. Then we get one of the roots. The first root here is -3. So where we're supposed to have m1, we simply replace it with -3. So -3 is put there. So we have c1e raised to the power -3x plus c2e raised to the power 4x. This becomes the general solution. So we've seen that this is this expression is the one that is followed when the roots of a characteristic equation are real but unequal. So these are real roots but not equal. Okay, let's move to the second example. The second example is d2y over dx2 minus 7 dy over dx minus 44y is equal to 0. So first step, we convert the given equation into the d notation. So it gives us this. Then to get the auxiliary equation, we simply get what is in the brackets, because we know that y cannot be equal to 0. So we get what is in the brackets, but then we replace d by m. So m squared minus dm minus 44 is equal to 0. So the roots of this equation, you can use different methods to solve the quadratic. The roots for this equation are m1 is equal to 11 and m2 is equal to -4. So the general solution then gives us y equals c1e raised to the power 11x plus c2e raised to the power -4x, where c1 and c2 are constants. So it doesn't mean all general solutions will have to use the letter c. At times you may find c is represented as K1, or C1 is represented as K1, C2 as K2. So any letter can be used to represent a constant. I think when we were doing the when we just started the topic on differential equations, you must have noticed that for the arbitrary constant of integration, we were using k. So there's no harm in you using k here as well. It's just one and the same thing. Okay, so we have these practice problems, and I expect each one of you to work them out. You work out, and you should be able to submit by the next lecture. So during the next lecture, ensure that you submit the solutions to these problems. Yeah, you can either submit to me directly in hard copy, or you can submit via the students portal. You can upload, then I'll be able to check. So this is very, very important. If you look at part A of the practice problems, these are just exactly like the two examples that we've worked out, or the three examples we've worked out. Then part B, it's similar to part A, but then there are conditions included. So we have these conditions that have been given. Okay, so let's work out these problems and submit through the students portal, or you can send them to me in hard copy, or whichever way you feel would be appropriate for you. Even WhatsApp, it's okay. You can convert your solution file to PDF and just send it over via WhatsApp. Okay, so this is where we end today's lecture on linear differential equations with constant coefficients. So those with any questions, you are free to bring them forward. You can text or use whatever means to find out which area you seem not to be clear of. Okay, so at this point we'll end our lecture. So please remember to take care of yourselves, stay at home, avoid crowded places, wash your hands frequently, don't touch your face. Remember always to observe social distancing. You know, coronavirus is real and it has come to our country. So we need to stay in our homes to avoid or to prevent the spread of the same. Okay, so best wishes to you. We end our lecture here. Until next time, goodbye.